Welcome! In this video, we're going to have a look at a specific set of domains where we can more or less easily extend our notion of integration over boxes computationally. So remember, we have just defined integration over arbitrary sets. And we have also seen that this definition comes with certain problems. There are sets that do not even have a well-defined volume or measure. So, of course, the question of how to compute an integral over these sets is not an easy one. That's why we are going to restrict ourselves to sets that have a somewhat nice description so that we can actually tackle the computation of integrals over these sets computationally. So that's going to be the goal of this video here. We'll consider sets that have a nice description, and these will be called normal domains. So let's define what we mean by nice description more precisely. We'll have a set D contained in R to the n. And we'll call that set a normal domain. If there is a description in the following way. Basically, you want to describe the set through a series of inequalities that build upon each other. So what we want is, we want to have first two real numbers. We'll simply call those real numbers alpha and beta. And let's say alpha is strictly less than beta. And those real numbers restrict one coordinate in this R to the n. We just take x1, but basically the order is of course arbitrary. And then for each of the following coordinates, we want to enclose the allowed values between a lower and an upper bound that depends on the coordinates that we had before. So formally, what we want is for each further coordinate, and for each I, we'll take I from 1 to n minus 1. You'd see in a minute why. For each of those indices, we want a continuous function. One for the lower bound, one for the upper bound. We'll call those alpha I and beta I. And they will be defined on R to the I and then map to R. And based on these functions, we want to be able to describe the set D in the following way. D consists of all points x of the form x1 to xn in R to the n, where the following are fulfilled. First we want is alpha is less or equal to x1 is less or equal to beta. So our two real numbers restrict the value of the first coordinate of that set. Also, the functions now restrict the values of the further coordinates, depending on those that we already have. So for the coordinate x2, we want a lower bound of alpha 1 of x1 and an upper bound of beta 1 of x1. Yeah, so those bounds may now depend on the value of x1. And so on. We'll extend that to the very last coordinate, xn. That will then be bounded by alpha n minus 1 of all the former coordinates. Alpha n minus 1 of x1 up to xn minus 1. And it will be bounded above by beta n minus 1 of x1 to xn minus 1. Okay, so that is formally the definition of a normal domain. Let's see a few examples to see how this is really applied. Yeah, it sounds pretty complicated. It really isn't. Just have to see a few actual examples to see how this is meant to be applied. So let's see. We'll start with a normal domain that we want to look like this. Let's have a coordinate system here. There's x1, there's x2. And let's say we want to describe the set that we're looking for using two parabolas. One looking like this, and the other one looking like this. Okay, so those are the functions. This one is the function x2 equals x1 squared, and this is the function x2 equals 1 minus x1 squared. And the set D that we want is the set enclosed here in the middle. Okay, so that is the domain that we want to describe. How do we do that? First thing we need to know is, of course, those points here. Where do these actually lie, or rather, what is the x1 coordinate of these points? Well, it's the intersection of the two parabolas. So that is exactly where x1 squared is equal to 1 minus x1 squared. Or in other words, where 2x1 squared is equal to 1. And that, of course, is the case if and only if x1 squared is 1 over 2, or x1 is plus or minus 1 over the square root of 2. Okay, so this is minus 1 over the square root of 2 and plus 1 over the square root of 2. So to describe this normal domain, we can say that x1 is enclosed between these two orange bounds, minus 1 over the square root of 2 and plus 1 over the square root of 2. And then x2 varies depending on the value of x1. So, for example, here, x2 doesn't have any variance at all, right? There's only one possible coordinate for x2 here. Whereas, for example, at this point here, x2 varies considerably between 0 and 1. So generally, there's an upper bound for x2, and that upper bound is given by this parabola. And there's a lower bound, and that is given by this parabola, depending on the current position of x1. So what does that mean for a set? It means the set D can be written in the following way. It consists of all x1, x2 in R2, where first the x1, so x1 is between minus 1 over square root of 2 and plus 1 over square root of 2. So those are the values for alpha and beta. And then, what about x2? Well, as I said, x2 is between those two parabolas. So the lower bound is x1 squared. It's less or equal to x2. The upper bound is 1 minus x1 squared. Okay, so those are the functions alpha 1 and beta 1. And that's a description of D in the set, in the form that we had in the definition. So that means D is a normal domain, because those functions here, alpha 1, beta 1, those are of course continuous. Okay, so this is a normal domain. First example. Let's have a second example. Let's say we want to integrate over a disk. That's a fairly common case. Okay, so again, let's draw a coordinate system. And then let's say we want our normal domain, want our set D to be a disk like this. Yeah, so a disk of radius 1 around the origin. That is our set D. Okay, so D is all x in R2, where the norm of x squared is less or equal to 1. Disk around the origin, let's just say with a radius 1. Is that a normal domain? And if so, how can we describe it as a normal domain? Well, again, we could start with the x1. Here, for example, there's the point -1, there's the point +1, so x1 varies between -1 and 1. That's an easy start. What about x2? If we want x2, then again, we'll have to find the description of the upper and lower bound depending on just x1. And here, for example, this here, this curve that would provide an upper bound for x2, depending on the current x1 value. Question is, of course, well, how can we describe that curve? And that's, again, not too hard. That norm of x squared, you know, that is x1 squared plus x2 squared. So that means on that curve, on that circle line, x2 squared is exactly equal to 1 minus x1 squared. And the 1 is the radius here, yeah? So for a different radius, it's not 1, but it might be the square of that radius. So in other words, x2 is plus or minus the square root of 1 minus x1 squared. And that's just what those curves here are. So that blue curve here, that is where x2 is plus the square root of 1 minus x1 squared. And let's draw that curve down here, that red curve here. That is where x2 is minus the square root of 1 minus x1 squared. So again, we can easily describe those boundaries for x2 in terms of x1. And that means we have our description of the set D. So D is all x equals x1, x2 in R2, where the following is true, where x1 varies between -1 and 1, so those are just constants, and x2 varies between the red lower bound, so minus square root of 1 minus x1 squared is less or equal to x2 is less or equal to that blue upper bound, square root of 1 minus x1 squared. So that is again a description in the form that we had in the definition. So that's a description as a normal domain. So also that circle, that is a normal domain. And finally, let's extend this to 3 dimensions, just as another quick example. Let's say we don't want a circle, let's say we want a unit ball. So all x in R3, where the norm of x squared is less or equal to 1. So the unit ball in R3. Then of course we can also use the same method here, right? Not going into the details here. I'll just let you know the results. So this is all x in R3. Again, x1 varies between -1 and 1. Then of course x2 is again restricted to that circle, right? So if we have a ball, if we cut that through the x1, x2 plane, then we get a circle. So that's where all the possible x2 values lie. So next restriction is the very same as we just had, minus the square root of 1 minus x1 squared is less or equal to x2 is less or equal to the square root of 1 minus x1 squared. And then of course x3 depends on x1 and x2. So depending on the value of those two have, we can vary the height over the x1, x2 plane, or the negative height. And in the same way as we discussed for the circle above, a lower bound is minus the square root of 1 minus x1 squared minus x2 squared. And an upper bound is the square root of 1 minus x1 squared minus x2 squared. So again, what you have here is a gradual buildup, right? So this is alpha beta, just reals. Here we have a function alpha 1 depending on x1 and beta 1 depending on x1. And here we have a function alpha 2 depending on x1 and x2, and beta 2 depending on x1 and x2. So again, we have this gradual buildup of the bounds for the different coordinates. And again, that means that unit ball is, of course, a normal domain in the sense of our definition. Just one thing I'd like to mention here is the choice of x1, x2, x3 is, of course, kind of arbitrary here. Yeah, you could also start with any other coordinate. For example, for this unit ball in the plane in R2. It doesn't really make any difference whether you start with x1 being bounded between those two coordinates, -1 and 1, or x2. You just start with x2 being bound between those two values, and then describe x1 as a function of x2, right? I just did it this way because that's how we are used to look at functions. But if it's easier the other way around, and we'll see examples where this is the case, then of course feel free to change the order of the coordinates any way you like. That's not a thing you're bound to. Okay, finally, let's get to the main theorem. of this section here. And that's a question: how do we use those normal domains for integration? How can we compute integrals over normal domains? And the answer is pretty much as you would expect. You could just, again, compute parameter integrals. But now you integrate out one variable after the other. And instead of having constant bounds like with the boxes, you now have bounds that depend on the remaining variables. So you substitute those bounds into the integral once again, and you have a function that kind of has lost one variable that you integrate out. And then you continue that process. So the order is not arbitrary anymore. It depends on the description that you chose for your set D. And of course, there might be several possibilities for that. But once you settle on the description for D for the normal domain, you're bound to that order for the integration. Okay, so let's write that down formally. And then again, we'll see some examples of how to do that. So here's the theorem. Let D be a normal domain in R to the n. And as usual, we'll denote the functions that we use for that normal domain by alpha I, beta I, and the reals by alpha beta. So let alpha beta be in R, and alpha I, beta I, let those be functions from Ri to R for I in 1 to n minus 1, be continuous functions that describe D, meaning D, the normal domain, is the set of all x1 to xn in R to the n, where alpha is less or equal to x1 is less or equal to beta, and alpha 1 of x1 is less or equal to x2 is less or equal to beta 1 of x1, and so on, up to alpha n minus 1 of x1 to xn minus 1 is less or equal to xn is less or equal to beta n minus 1 of x1 to xn minus 1. So that's the description of our normal domain. And the theorem says then a continuous function over that normal domain is Riemann integrable, and the integral can be evaluated by just evaluating the parameter integrals with variable bounds in the right order. Then a continuous function f defined on D, mapping to the reals, is Riemann integrable over D with, and that's the main result now, the result of that integral is integral of f of x dx over D. Again, you start with the innermost integral by integrating over xn, and you have boundaries depending on x1 to xn minus 1, those alpha n minus 1, beta n minus 1. And then you iterate until you get to the outermost integral where just x1 is left, and that has constant boundaries. So the outermost integral is the 1 over x1 from alpha to beta. Then the next one inside here is the 1 over x2 over alpha 1 x1 to beta 1 x1. So the result still contains an x1. And so on, until you get to the innermost integral. That's the 1 over xn, with boundaries now depending on x1 to xn minus 1. And you integrate the function f of x1, x2 up to xn. And as I said, innermost integral dxn. And then you integrate your way out until finally you integrate out this x1, where you just have constant bounds anymore. So per integration step, you lose one of the variables. And again, the order is not arbitrary anymore. Once you fix the description of d, then that gives you the order for the integration. You might have freedom in fixing that description of d, of course, yeah? Usually there's more than one possible description for a normal domain, and that means you might exchange the order in that description and thus in the integral as well. But those depend on each other. Once you're fixed on a description for d, then you're fixed for the order of the integral. Okay, so that's how integration over normal domains work. And in one of the next videos, we're going to see a couple of examples to demonstrate you how this is done. I'll see you then.